somewhere in the silent darkness of space, two of the most extreme objects in the universe begin to drift toward each other. One is a neutron star, a city-sized sphere holding more mass than our Sun. The other, a black hole, a region of space where gravity becomes so powerful that not even light can escape. When these two monsters meet, the universe does not stay quiet. Space-time bends. Radiation explodes outward. Matter is torn apart at atomic scales, and for a few violent seconds the cosmos releases more energy than entire galaxies produce in years. Tonight, we are going to witness what really happens when a black hole eats a neutron star. Not in science fiction, but in real physics, real observations, and terrifying cosmic reality. If you enjoy deep space mysteries, extreme cosmic events, and science documentaries that push the limits of reality, make sure to subscribe now and turn on notifications, because the universe is far more dangerous and fascinating than most people realize. Now, get comfortable, because what happens next unfolds at the edge of gravity itself.
In the deepest regions of space, far beyond the reach of ordinary stars and planets, neutron stars and black holes exist as remnants of massive stellar deaths. They are not created quietly. They are born in violence. When a giant star exhausts its nuclear fuel, gravity overwhelms its core. The outer layers explode outward in a supernova, while the center collapses inward. If the core is heavy enough, it becomes a neutron star. If it is heavier still, it collapses even further and forms a black hole. These objects are the extreme endpoints of stellar evolution, and when their paths cross, the universe experiences one of the most dramatic events physics can produce. A neutron star is one of the densest objects in existence. It is usually only about 20 kilometers across, yet it contains more mass than the Sun. Inside it, atoms are crushed so tightly that electrons and protons merge into neutrons. Matter is packed so densely that a single teaspoon of neutron star material would weigh billions of tons on Earth. Gravity on its surface is so intense that mountains cannot form. Even small bumps are flattened instantly. The star becomes almost perfectly smooth, shaped only by rotation and magnetic forces. Despite this incredible density, neutron stars are still physical objects with solid structure. They have a crust made of nuclear matter, a superfluid interior, and powerful magnetic fields that can be trillions of times stronger than Earth's. Many neutron stars spin rapidly, rotating hundreds of times per second. As they rotate, they emit beams of radiation that sweep across space like cosmic lighthouses. These are known as pulsars, and they are among the most precise natural clocks in the universe. Black holes, on the other hand, represent an even more extreme outcome. When gravity overwhelms all known forces, the collapsing core of a star shrinks beyond any physical surface. The result is a region of space-time where gravity becomes infinite at the center, surrounded by a boundary called the event horizon. Once matter crosses this boundary, it can never escape. Not even light can return. From the outside, a black hole appears as a dark sphere surrounded by distorted space-time, bending light and warping the paths of nearby objects. Although black holes seem empty, they are anything but simple. Their gravity affects everything around them. They can pull in gas, dust, stars, and even entire star systems. When material falls toward a black hole, it does not immediately disappear. Instead, it forms a spinning disk called an accretion disk. Friction and compression inside this disk heat the material to millions of degrees, causing it to glow brightly in X-rays and other forms of radiation. In some cases, black holes also produce powerful jets that shoot matter outward at near light speed. Now imagine these two cosmic extremes approaching each other. a neutron star, and the black hole orbiting in a binary system. Such systems form when two massive stars are born together and evolve side by side. Over millions of years, both stars explode in supernovae, leaving behind a neutron star and a black hole locked in a gravitational dance. At first, they orbit each other at safe distances, but over time, they lose energy by emitting gravitational waves. These are ripples in spacetime predicted by Einstein's theory of general relativity and directly observed for the first time in 2015. As gravitational waves carry energy away from the system, the orbit slowly shrinks. The neutron star and black hole spiral closer and closer together. Their orbital speed increases. Each revolution becomes faster than the last. In the final moments before collision, they can orbit each other dozens of times per second. Space-time itself vibrates with their motion. If detectors on Earth are tuned correctly, scientists can measure these vibrations across billions of light years. As the neutron star approaches the black hole, tidal forces begin to stretch it. Just as the moon pulls on Earth's oceans to create tides, the black hole's gravity pulls unevenly on different parts of the neutron star. The side closer to the black hole feels stronger gravity than the far side. This difference creates intense stretching. The neutron star begins to deform from a sphere into an elongated shape, like a drop of liquid being pulled downward. At a certain distance, the black hole's tidal forces become stronger than the neutron star's own gravity. When this happens, the neutron star cannot hold itself together. It begins to tear apart. This process is known as tidal disruption. The crust cracks. Nuclear matter is ripped free. Streams of ultra-dense material spiral away from the neutron star and fall toward the black hole. What happens next depends on the size and spin of the black hole. If the black hole is very massive, the neutron star may cross the event horizon before it is fully torn apart. In this case, the neutron star disappears almost instantly, leaving little visible matter behind. The merger produces a powerful gravitational wave signal, but relatively little electromagnetic radiation. If the black hole is smaller or spinning rapidly, the neutron star can be shredded outside the event horizon. In this scenario, enormous amounts of matter are thrown into space before being consumed. This creates a bright, short-lived explosion known as a kilonova. During this event, heavy elements such as gold, platinum and uranium are formed through rapid nuclear reactions. These elements are then scattered into space, eventually becoming part of future stars, planets, and possibly living organisms. The moment of merger is one of the most violent events in the universe. In just a few seconds, energy equivalent to several solar masses is released in the form of gravitational waves. These waves travel across the universe at the speed of light, stretching and compressing space-time as they pass. When they reach Earth, they cause distances to change by less than the width of a proton. Yet, with incredibly sensitive instruments, scientists can detect these tiny distortions and reconstruct the details of the collision. At the same time, bursts of gamma rays and X-rays may be emitted. These signals allow astronomers to locate the event in the sky and study its aftermath. Telescopes across the world turn toward the source, observing the fading glow of the explosion. This combination of gravitational wave detection and electromagnetic observation is known as multi-messenger astronomy. It allows scientists to study cosmic events in multiple ways at once. After the neutron star is consumed, the black hole grows more massive. It now carries the combined mass of both objects. Any remaining debris continues to orbit briefly before falling inward or being ejected into space. The surrounding region becomes temporarily chaotic, filled with radiation, shock waves, and distorted magnetic fields. Over time, the system stabilizes. The black hole settles into a new state, quietly drifting through space. The intense radiation fades. The gravitational waves pass on, continuing their journey across the universe long after the event itself is over. Yet even after the visible explosion ends, the consequences remain. The heavy elements created during the merger spread outward, enriching nearby interstellar clouds. These materials will eventually become part of new stars and planetary systems. In this way, the destruction of a neutron star contributes to the creation of future worlds. This process reveals a deeper truth about the universe. Even the most violent events play a role in cosmic balance. Destruction and creation are connected. Black holes do not simply erase matter. They transform it, redistribute it, and influence the structure of galaxies. When a black hole eats a neutron star, it is not just a collision. It is a fundamental interaction between gravity, nuclear physics, and space-time itself. It tests the limits of our understanding. It reveals how matter behaves under extreme conditions that cannot be replicated on Earth. Scientists continue to study these events to answer some of the deepest questions in physics. How does matter behave at nuclear densities? How does gravity operate at extreme strengths? What happens to information when matter crosses the event horizon? Each neutron star merger provides new data that brings us closer to understanding the nature of reality. In the next phase of this cosmic story, we move deeper into the aftermath. We explore what happens to the space around the black hole, how the environment changes, and how these mergers influence the evolution of galaxies themselves. After the initial collision between a black hole and a neutron star, the universe does not immediately return to silence. The aftermath is filled with motion, radiation, and long-lasting changes that ripple outward through space. What remains is not simply a larger black hole, but an altered region of space-time carrying the memory of one of the most extreme events nature can produce. When the neutron star is torn apart, a portion of its matter does not fall directly into the black hole. Instead, it forms a swirling disk of debris around the event horizon. This temporary structure, known as an accretion disk, is made of nuclear matter heated to extraordinary temperatures. Friction between particles, magnetic turbulence, and intense gravitational compression cause the disk to glow across the electromagnetic spectrum. X-rays, gamma rays, and ultraviolet radiation pour outward into space. Inside this disk, matter spirals inward at tremendous speed. As it falls closer to the event horizon, it accelerates, releasing more energy with every orbit. The closer the material gets, the hotter and brighter it becomes. Temperatures can rise to billions of degrees. Under these conditions, atoms are stripped apart. Nuclei collide. Particles exist in exotic states rarely seen elsewhere in the universe. At the same time, powerful magnetic fields twist and stretch around the spinning black hole. These magnetic fields can channel some of the infalling matter into narrow beams that shoot outward from the black hole's poles. These jets travel at speeds approaching that of light and can extend thousands of light years into surrounding space. Although the neutron star itself is destroyed, its matter helps power these jets, spreading energy far beyond the site of the collision. The region around the merger becomes one of the most energetic environments known. Shock waves ripple outward, compressing nearby gas clouds. Radiation heats surrounding material. Magnetic fields become tangled and unstable. For a brief period, this area outshines entire galaxies in specific wavelengths. Over time, the intensity begins to fade. The accretion disk slowly drains as matter falls into the black hole or escapes into space. The jets weaken. Radiation levels drop. What remains is a newly formed black hole surrounded by altered space-time and scattered debris. Yet, the influence of the event extends much further than the immediate surroundings. The gravitational waves produced during the merger continue traveling across the universe. They pass through galaxies, star systems, and even Earth itself. These waves carry detailed information about the masses, spins, and structure of the merging objects. By analyzing these signals, scientists can reconstruct the entire event from the final spiral to the moment of collision. This ability to detect gravitational waves has transformed modern astronomy. Before these detections, black hole and neutron star mergers were invisible except through rare bursts of radiation. Now, researchers can observe them directly through space-time itself. Each detection provides new insight into how matter behaves under extreme gravity. One of the most important discoveries from these events is confirmation of Einstein's theory of general relativity under extreme conditions. The way space-time warps and vibrates during these mergers matches theoretical predictions with remarkable precision. This confirms that gravity behaves as expected even in the strongest gravitational fields known. At the same time, neutron star mergers offer clues about the nature of ultra-dense matter. The internal structure of neutron stars is still not fully understood. Scientists do not yet know exactly how neutrons arrange themselves at such extreme pressures. When a neutron star is torn apart, the gravitational wave signal contains subtle features that reflect its internal stiffness and composition. By studying these patterns, researchers can learn about matter at densities far beyond anything achievable in laboratories. The creation of heavy elements during these mergers also has long-term consequences. When neutron-rich material is ejected into space, it undergoes rapid nuclear reactions that build heavy atomic nuclei. Gold, platinum and other rare elements are forged in these violent conditions. Over millions of years, these materials spread through galaxies, becoming part of interstellar clouds that later form new stars and planets. This means that many of the heavy elements found on Earth likely originated in ancient neutron star mergers. Jewelry, electronics, and even components of the human body may contain atoms created during cosmic collisions billions of years ago. In this way, the destruction of a neutron star contributes directly to the building blocks of life. Another lasting effect is the influence these mergers have on galactic environments. When jets and radiation interact with surrounding gas, they can trigger or suppress star formation. In some regions, shock waves compress gas clouds, encouraging new stars to form. In others, intense radiation heats the gas and prevents it from collapsing. Over long periods, these interactions help shape the structure and evolution of galaxies. The black hole itself also changes after consuming a neutron star. Its mass increases, and its spin may change depending on the direction and angle of the merger. A rapidly spinning black hole can store enormous rotational energy. This energy can be extracted through magnetic interactions and converted into powerful jets. The merger, therefore, affects not only the black hole's size, but also its future behavior. As time passes, the black hole settles into a more stable state. It becomes quieter, pulling in only small amounts of surrounding matter. To distant observers, it appears as a dark, silent object drifting through space. Yet beneath this calm appearance lies the memory of its violent past. These mergers also challenge scientists to understand what happens to information when matter falls into a black hole. According to quantum physics, information cannot be destroyed. According to classical black hole physics, anything that crosses the event horizon is lost forever. This contradiction is known as the black hole information paradox. Neutron star mergers provide real-world scenarios where massive amounts of structured matter disappear into black holes. Studying these events may help resolve this long-standing puzzle. Another important aspect of these collisions is their role in testing alternative theories of gravity. Some theories predict subtle differences in how gravitational waves behave. By comparing observations with predictions, scientists can rule out incorrect models and refine our understanding of fundamental physics. The detection of black hole and neutron star mergers has also improved our ability to measure cosmic distances. Gravitational wave signals act as natural measuring tools. By analyzing the signal strength and shape, researchers can estimate how far away the event occurred. When combined with traditional astronomical observations, this helps refine measurements of the universe's expansion rate. This connects neutron star mergers to one of the biggest questions in cosmology: how fast the universe is expanding and how that expansion is changing over time. In this way, a single violent collision can contribute to understanding the large-scale behavior of the entire cosmos. As technology improves, scientists expect to detect many more of these events, New observatories will be more sensitive and able to detect weaker and more distant mergers. This will allow researchers to build large statistical samples and identify patterns in how often these collisions occur, where they happen, and what conditions produce them. With enough data, scientists may uncover new classes of exotic objects, such as unusually massive neutron stars or black holes with extreme spins. They may also observe rare variations in merger behavior, revealing new physical processes. Despite the incredible energy involved, these events are extremely rare on human timescales. In a single galaxy like the Milky Way, such mergers may occur only once every tens of thousands of years. Yet across the vast universe, containing hundreds of billions of galaxies, they happen regularly. At any given moment, somewhere in the cosmos, a neutron star is likely being consumed by a black hole. This perspective highlights the immense scale of the universe. Events that seem rare locally become common when viewed across cosmic distances. The universe is constantly changing, evolving through countless interactions that reshape matter and energy. When we observe these mergers from Earth, we are witnessing ancient history. The signals we detect today may have travelled for billions of years before reaching our instruments. The collision itself may have occurred long before Earth even formed. Yet its effects arrive now, allowing us to study a past moment frozen in space-time. This connection between past and present reveals something profound about astronomy. Looking into space is also looking into time. Each detection is a message from the distant past, carrying information about conditions that existed long ago. As we move deeper into understanding these events, we begin to see that black holes and neutron stars are not isolated curiosities. They are part of a larger cosmic ecosystem. Their interactions influence galaxies, distribute elements, test physical laws, and shape the structure of the universe. In the next phase of this story, we will explore what these mergers reveal about the ultimate fate of matter, the limits of physics, and the strange behavior of space-time near the event horizon itself. When a black hole consumes a neutron star, the most dramatic action happens in the moments closest to the event horizon. This region represents the boundary between what the universe can observe and what is forever hidden. It is here that the laws of physics are pushed to their limits, and where scientists focus their attention to understand how reality behaves under extreme conditions. As matter from the neutron star spirals inward, it experiences intense gravitational acceleration. Time itself begins to behave differently. According to general relativity, the stronger the gravity, the slower time moves relative to distant observers. Near the event horizon, this effect becomes extreme. To an outside observer, the infalling matter appears to slow down, becoming dimmer and redder as its light is stretched by gravity. Eventually, it seems to freeze at the edge of the black hole, fading from view. In reality, from the perspective of the falling matter, the journey continues without pause. The difference between these viewpoints reveals how gravity reshapes the experience of time. As the neutron star's material crosses the event horizon, it is no longer visible to the outside universe. However, the effects of its presence remain. The black hole's mass increases, its gravitational pull becomes stronger, its rotation may change. These measurable changes provide indirect evidence of what has fallen inside. Inside the event horizon, our current theories cannot fully describe what happens. According to classical physics, all infalling matter continues toward the singularity, a region where density becomes infinite and known physical laws break down. The neutron star's matter is compressed beyond any recognizable structure. At this scale, the distinction between particles disappears. Matter and energy become part of a state we do not yet understand. This unknown interior is one of the greatest mysteries in physics. Scientists suspect that quantum effects become important near the singularity. However, a complete theory that combines gravity and quantum mechanics has not yet been developed. Neutron star mergers provide real examples of matter entering this unknown regime, making them valuable test cases for future theories. One of the most puzzling questions is what happens to the information contained in the neutron star. Information refers to the arrangement of particles, their quantum states, and the structure of matter. According to quantum theory, information cannot be destroyed, yet black holes seem to erase information by hiding it behind the event horizon. This contradiction is known as the black hole information paradox. When a neutron star is consumed, vast amounts of structured matter disappear from view. Does the information vanish forever, or is it preserved in some form? Some theories suggest that information is encoded on the surface of the event horizon. Others propose that it is slowly released through a process known as Hawking radiation, a faint emission predicted to occur over extremely long timescales. Neutron star mergers provide new ways to study this problem. By observing how black holes grow and evolve after consuming neutron stars, scientists can test predictions about how information might be stored or released. While direct observation of the interior remains impossible, subtle effects in radiation and gravitational signals may offer indirect clues. Another fascinating aspect of these events is the behavior of spacetime itself. During the final moments of merger, spacetime becomes highly distorted. Waves ripple outward. The shape of the event horizon changes as mass and spin are added. These distortions create unique gravitational wave signatures that can be measured and analysed. By studying these signatures, scientists can determine how the black hole responds to the sudden influx of matter. This helps test whether black holes behave exactly as predicted by general relativity, or whether new physics emerges under extreme conditions. The intense gravity near the event horizon also affects light in dramatic ways. Photons passing near the black hole are bent along curved paths. Some are captured, others are redirected, creating warped images of surrounding space. In some cases, light can orbit the black hole temporarily before escaping. This creates bright rings and distorted shapes that telescopes can observe. When a neutron star is disrupted near a black hole, the resulting debris and radiation interact with this curved space-time. Light emitted from the accretion disk is stretched and bent, producing unique spectral signatures. These patterns allow astronomers to measure the black hole's spin and mass with high precision. The merger also creates extreme magnetic environments. Neutron stars possess powerful magnetic fields, and when their material is torn apart, these fields become tangled and amplified. As this magnetized plasma falls into the black hole, it interacts with the black hole's rotation, generating electric currents and accelerating particles to high energies. These processes can produce bursts of radiation that are detectable across vast distances. Gamma-ray flashes, X-ray afterglows, and radio emissions provide additional information about the physical conditions near the event horizon. By combining these observations with gravitational wave data, scientists can build a more complete picture of the merger. Another important consequence of these events is their role in testing the limits of matter stability. Neutron stars represent the maximum density at which matter can exist without collapsing into a black hole. When a neutron star is disrupted, scientists can observe how matter behaves as it transitions from a stable state into gravitational collapse. This helps refine models of nuclear physics and the equation of state that describes ultra-dense matter. Understanding this transition is important not only for astrophysics but also for fundamental physics. It provides insight into how particles behave under extreme pressure and temperature, conditions similar to those that existed shortly after the Big Bang. The merger also influences the surrounding interstellar environment. Radiation and shock waves propagate outward, heating nearby gas clouds and altering their chemical composition. Over time, these effects can change the structure of the region and influence future star formation. In some cases, the merger can create long-lasting remnants, such as expanding shells of energized gas. These structures can persist for thousands of years, slowly dissipating into the surrounding medium. They serve as markers of past cosmic events, leaving behind physical evidence of ancient collisions. The black hole that remains after the merger may also become part of larger gravitational systems. It can later merge with other black holes or neutron stars, participating in even more powerful events. Over cosmic timescales, these repeated mergers contribute to the growth of supermassive black holes found at the centers of galaxies. This process connects small-scale stellar remnants to the largest structures in the universe. A neutron star consumed in a distant galaxy today may contribute through a chain of mergers to the formation of a black hole millions or billions of times more massive than the Sun. Another profound implication of these events is their role in shaping cosmic evolution. By redistributing energy and matter, mergers influence the thermal and chemical history of galaxies. They help determine where heavy elements are found and how gas clouds evolve. The study of black hole and neutron star mergers is still in its early stages. Each new detection provides more data, refining models and revealing unexpected details. Some mergers show unusual behavior, such as delayed radiation signals or unexpected element production. These anomalies challenge existing theories and push scientists to develop more accurate descriptions. As observational technology advances, scientists will be able to observe these events in greater detail. Future gravitational wave detectors will be more sensitive and capable of detecting mergers at greater distances. Space-based observatories will provide clearer views of high-energy radiation produced during these collisions. With these tools, researchers hope to answer some of the deepest questions in physics. What is the true nature of space-time near a black hole? How does matter behave at extreme density? How is information preserved in the universe? When a black hole eats a neutron star, the event is not only a dramatic cosmic collision, it is a natural experiment conducted by the universe itself. It reveals how gravity, matter, energy, and time interact at the most extreme scales. Each merger adds a new piece to the puzzle of reality. It shows that even in the darkest regions of space, powerful processes are at work, shaping the universe in ways we are only beginning to understand. In the next part, we will explore how these extreme events may help scientists uncover new laws of physics and how future observations could change our understanding of the cosmos itself. As scientists continue to study black hole and neutron star mergers, a new layer of understanding begins to form. These events are not only spectacular collisions, they are windows into physics that cannot be tested on Earth. They allow researchers to explore gravity at its strongest, matter at its densest, and space-time at its most distorted. One of the most important scientific opportunities created by these mergers is the ability to test general relativity in extreme environments. Einstein's theory has been confirmed many times in weak gravitational fields, such as those around planets and stars. But near black holes, gravity becomes so intense that even small deviations from theoretical predictions would become noticeable. By analysing gravitational wave signals from mergers, scientists can measure how space-time behaves under these extreme conditions. So far, observations have shown remarkable agreement with Einstein's predictions. The shape of the gravitational waves, the rate of orbital decay, and the final vibration patterns of newly formed black holes all match theoretical models with high precision. This strengthens confidence in general relativity, while also setting tight limits on alternative theories of gravity. However, scientists continue to search for subtle anomalies. Even tiny differences in signal behavior could point toward new physics. Some theories predict extra dimensions, modified gravity, or exotic particles that could influence merger dynamics. Each new detection offers another opportunity to test these ideas. Another major area of interest is the study of black hole spin. When a neutron star merges with a black hole, the direction and speed of rotation can change significantly. Spin affects how space-time twists around the black hole, influencing the formation of accretion disks and jets. By analysing radiation patterns and gravitational wave data, researchers can estimate how fast the black hole is rotating after the merger. Understanding black hole spin is important because it influences how black holes interact with their surroundings. Rapidly spinning black holes can extract energy from their own rotation through magnetic processes, powering some of the most energetic phenomena in the universe. These include quasars and active galactic nuclei, which emit enormous amounts of radiation and shape the evolution of entire galaxies. Neutron star mergers also provide insight into the behavior of matter under extreme pressure. The internal structure of neutron stars remains one of the biggest unknowns in astrophysics. Scientists know that neutron stars are composed primarily of neutrons, but the exact arrangement of particles inside them is uncertain. Some models suggest the presence of exotic states of matter, such as quark matter or hyperons. When a neutron star is torn apart during a merger, the gravitational wave signal carries information about how easily the star deforms. This property, known as tidal deformability, depends on the internal stiffness of the neutron star. By measuring this parameter, scientists can narrow down which models of dense matter are most accurate. These measurements bring researchers closer to understanding the fundamental behavior of nuclear matter. They provide real-world data from conditions far beyond those achievable in particle accelerators. In this sense, neutron star mergers serve as natural laboratories for extreme physics. Another important consequence of these events is their role in mapping the population of compact objects in the universe. By detecting multiple mergers, scientists can estimate how common black holes and neutron stars are, how often they form binary systems, and how frequently they collide. This information helps refine models of stellar evolution and galaxy formation. The distribution of merger events also reveals how stars are born and die in different environments. Some galaxies produce more massive stars than others. Some regions are more likely to host binary systems. By studying merger rates across cosmic distances, researchers gain insight into how galaxies evolve over billions of years. Neutron star and black hole mergers also contribute to understanding cosmic chemical evolution. Heavy elements produced during these collisions spread through interstellar space and become incorporated into future generations of stars and planets. Over time, this process enriches galaxies with metals, changing the composition of planetary systems and influencing the potential for life. By measuring the abundance of heavy elements in different regions, scientists can trace the history of merger events and their contribution to cosmic chemistry. This helps explain why some galaxies contain higher concentrations of rare elements than others. Another fascinating aspect of these mergers is their effect on surrounding space-time geometry. When two massive objects collide, the curvature of space-time changes dynamically. The newly formed black hole vibrates briefly as it settles into a stable shape. This phase, known as the ringdown, produces a distinctive gravitational wave signal. By analysing ringdown signals, scientists can test whether black holes follow the predictions of general relativity. According to theory, the vibration patterns depend only on the black hole's mass and spin. Any deviation could indicate new physics or previously unknown properties of space-time. So far, ringdown observations have matched theoretical expectations. However, future detectors with greater sensitivity may reveal subtle effects that were previously undetectable. The merger environment also influences high-energy particle acceleration. Magnetic fields and shock waves created during the collision can accelerate particles to near-light speed. These particles may contribute to cosmic rays that travel across the galaxy and occasionally reach Earth. Studying these processes helps scientists understand the origins of high-energy cosmic radiation and how energy is transferred between different forms during extreme astrophysical events. Another area of research focuses on the interaction between merger events and surrounding star-forming regions. In some cases, radiation and shock waves can compress nearby gas clouds, triggering new star formation. In other cases, intense radiation can heat gas and prevent it from collapsing. The balance between these effects influences how galaxies grow and evolve. Understanding this interaction is important for building accurate models of galaxy formation. It shows that compact object mergers are not isolated events. They actively shape their cosmic environment. The long-term evolution of black holes after mergers is also an active area of study. Over millions and billions of years, black holes may undergo multiple mergers, gradually growing in mass. These processes contribute to the formation of supermassive black holes found at the centers of galaxies. By studying small-scale mergers, scientists gain insight into how large-scale cosmic structures develop. The growth of black holes is connected to the growth of galaxies themselves, forming a complex feedback loop that influences cosmic history. Another intriguing possibility is the detection of intermediate mass black holes formed through repeated mergers. These objects, larger than stellar black holes but smaller than supermassive ones, have been difficult to observe. Neutron star and black hole mergers may provide a pathway to their formation. If detected in significant numbers, intermediate mass black holes would help bridge the gap between known black hole populations and improve understanding of black hole evolution. The study of these events also influences the design of future observatories. Scientists are developing more sensitive gravitational wave detectors, both on Earth and in space. These instruments will allow detection of weaker signals and observation of mergers at greater distances. Space-based detectors will be particularly valuable for studying low-frequency gravitational waves produced by massive black hole mergers. Combined with ground-based detectors, they will provide a more complete picture of gravitational wave astronomy. As observational capabilities improve, scientists expect to uncover new classes of merger events. Some may involve unusual combinations of objects, such as neutron stars merging with highly spinning black holes, or systems with extreme mass ratios. Each new type of event will offer fresh insights into physics. Another important aspect is the role of artificial intelligence and advanced data analysis techniques. Gravitational wave signals are weak and buried in noise. Machine learning algorithms help identify patterns and extract meaningful information from large datasets. These tools allow faster detection and more accurate interpretation of merger events. This combination of advanced technology and theoretical modeling is accelerating progress in astrophysics. It allows scientists to move beyond simple detection and toward detailed understanding of each event. Black hole and neutron star mergers represent a turning point in astronomy. They allow direct observation of phenomena that were once purely theoretical. They connect abstract equations with real cosmic events. When a black hole eats a neutron star, the universe performs a natural experiment on the largest possible scale. It reveals how gravity, matter, and space-time interact under extreme conditions. Each event adds a new chapter to the story of cosmic evolution. As research continues, these mergers will help answer some of the deepest questions about the nature of reality. They show that even in the darkest regions of space, powerful processes shape the universe in ways that are both violent and profoundly informative. In the next part, we will explore how these discoveries may influence future theories of physics, and how our understanding of black holes could change as new data continues to arrive. As research into black hole and neutron star mergers advances, scientists are beginning to realize that these events may reshape our understanding of physics itself. What once seemed like isolated cosmic catastrophes are now seen as crucial experiments that test the limits of everything we know about matter, gravity, and the structure of reality. One of the most exciting possibilities emerging from these mergers is the opportunity to explore the boundary between classical physics and quantum mechanics. Black holes represent regions where gravity is extremely strong, while neutron stars contain matter compressed to quantum-scale densities. When these two objects interact, both regimes collide in a single event. This creates conditions where general relativity and quantum physics must work together, even though no complete theory currently unites them. Physicists believe that understanding this boundary could lead to a theory of quantum gravity, a framework that explains how space-time behaves at the smallest scales. Neutron star mergers provide real-world data from environments that resemble the early universe, where temperatures and densities were extreme. By studying gravitational waves and radiation produced during these events, scientists hope to uncover clues about how space-time behaves at the most fundamental level. Another major area of interest is the possibility that mergers could reveal the existence of exotic forms of matter. Some theories predict that neutron stars may contain strange matter, quark matter, or other unknown states. When a neutron star is torn apart, these exotic materials could briefly exist outside the star, leaving unique signatures in gravitational wave signals and electromagnetic radiation. Detecting such signatures would provide the first direct evidence of new forms of matter. This would transform nuclear physics and deepen understanding of how particles behave under extreme pressure. It would also connect astrophysics with particle physics in powerful new ways. Black hole mergers also provide insight into the nature of horizons and space-time boundaries. The event horizon is not a physical surface, yet it behaves like a one-way barrier. Understanding how matter interacts with this boundary could reveal new information about causality, time, and the flow of information. Some theoretical models suggest that event horizons may not be perfectly smooth. Instead, they could possess microscopic structure influenced by quantum effects. If this is true, subtle differences in merger behavior might be detectable in gravitational wave patterns. Searching for these deviations is one of the goals of future high-precision detectors. Another fascinating possibility involves the role of black holes in testing fundamental constants of nature. Physical constants such as the speed of light and the strength of gravity appear to be fixed throughout the universe. However, some theories suggest they could vary slightly under extreme conditions. By observing black hole mergers, scientists can test whether these constants remain unchanged even in the strongest gravitational fields. Neutron star and black hole mergers also influence the study of time itself. The extreme gravitational time dilation near black holes allows scientists to observe how time behaves in environments far beyond everyday experience. These observations help confirm that time is not absolute, but relative depending on gravity and motion. This understanding has practical implications beyond astrophysics. Technologies such as GPS already rely on relativistic corrections to function accurately. Continued study of extreme gravity may lead to improved models of time measurement and synchronization, influencing future technological systems. Another important impact of merger research is its contribution to understanding the universe's expansion. Gravitational wave events can be used as cosmic distance markers. By comparing gravitational wave data with electromagnetic observations, scientists can measure how fast the universe is expanding. This method offers an independent way to calculate the Hubble constant, a value that describes the rate of cosmic expansion. Current measurements using different techniques do not fully agree. Neutron star mergers provide a new approach that could help resolve this tension and refine cosmological models. Black hole and neutron star mergers also contribute to understanding dark matter and dark energy. While these mysterious components make up most of the universe's mass and energy, their nature remains unknown. Some theories predict that dark matter may interact weakly with compact objects, influencing merger behavior. By studying large numbers of mergers, scientists may detect subtle statistical patterns that reveal the presence of dark matter. Similarly, observing how gravitational waves propagate through expanding space-time can provide insight into the properties of dark energy. Another area of exploration is the possibility of detecting primordial black holes. These hypothetical objects may have formed shortly after the Big Bang. If they exist, they could occasionally merge with neutron stars. Such events would produce unique gravitational wave signatures different from ordinary stellar black hole mergers. Detecting primordial black holes would have profound implications for cosmology. It would provide direct evidence of early universe conditions and offer clues about inflation and cosmic structure formation. The study of mergers also influences our understanding of stellar evolution. By analysing the masses and spins of merging objects, scientists can trace back the life cycles of the stars that created them. This helps refine models of how massive stars form, evolve, and collapse. These insights improve predictions about supernova explosions, star formation rates, and the distribution of compact objects across galaxies. They also help identify which environments are most likely to produce neutron star and black hole binaries. Another long-term effect of merger research is its role in inspiring new technology. Detecting gravitational waves requires extremely precise instruments capable of measuring distances smaller than the width of an atom. Developing this technology has pushed advances in laser physics, vibration isolation, data analysis, and quantum measurement techniques. These technological innovations often find applications outside astronomy. Improved sensors, precision measurement tools, and advanced computing methods benefit fields such as medicine, engineering, and communications. The cultural impact of these discoveries is also significant. Observing black hole and neutron star mergers changes how humanity views the universe. It reveals that space-time itself is dynamic, flexible, and responsive to cosmic events. This challenges the traditional idea of space as empty and static. Public interest in these discoveries has grown rapidly. Images of black holes, animations of mergers, and reports of gravitational wave detections capture imagination and inspire curiosity. This renewed interest in science encourages education and exploration, shaping future generations of researchers. Another important consequence is the development of international scientific collaboration. Gravitational wave observatories operate as global networks. Researchers from many countries share data and coordinate observations. This collaboration strengthens scientific progress and promotes peaceful cooperation across borders. Black hole and neutron star mergers also help refine computational modeling techniques. Simulating these events requires enormous computing power and advanced algorithms. Improvements in numerical relativity and simulation software contribute to progress in other areas of physics and engineering. As more mergers are observed, scientists can build comprehensive catalogues of events. These catalogues allow statistical analysis that reveals trends in mass distribution, spin alignment, and merger frequency. Such patterns provide insight into how compact objects form and interact over cosmic time. This growing database will allow researchers to test competing theories and refine models of astrophysical processes. Over time, the picture of how black holes and neutron stars shape the universe will become clearer and more detailed. Another fascinating aspect is the role of mergers in shaping cosmic structure. Energy released during these events influences the surrounding environment, contributing to feedback processes that regulate star formation and galaxy growth. Over billions of years, repeated mergers play a subtle but important role in the evolution of cosmic ecosystems. Black holes themselves may serve as anchors around which galaxies form and evolve. Understanding how they grow through mergers helps explain why supermassive black holes are found at the centers of most galaxies. Neutron star mergers also provide clues about the origin of cosmic magnetic fields. The intense magnetic activity during these events may contribute to the generation and amplification of large-scale magnetic structures observed in galaxies. Another long-term implication is the potential role of mergers in creating rare astrophysical phenomena such as fast radio bursts. Some theories suggest that interactions between neutron star debris and black hole magnetic fields could produce short, intense radio pulses. Continued observation may help determine whether these events are connected. As the study of these mergers progresses, it becomes clear that they are not isolated events. They are deeply connected to many aspects of cosmic evolution, from the formation of elements to the growth of galaxies and the behavior of space-time itself. When a black hole eats a neutron star, it is not simply a moment of destruction. It is a powerful transformation that influences the universe on multiple levels. It creates new matter, tests physical laws, and shapes the future of cosmic structures. With each new observation, scientists move closer to answering fundamental questions about the nature of reality. These events serve as reminders that the universe is not static or quiet. It is alive with motion, energy, and continuous transformation. In the next stage of this exploration, we will look at how future observatories and upcoming missions could revolutionize the study of these extreme events, and what new discoveries may lie ahead. As humanity looks toward the future of astrophysics, black hole and neutron star mergers are expected to become one of the most powerful tools for unlocking the deepest secrets of the universe. What was once invisible is now measurable. What was once theoretical is now observed. And with every new detection, the boundary of human knowledge expands a little further. One of the most important developments shaping this future is the next generation of gravitational wave observatories. Current detectors have already transformed astronomy, but they represent only the beginning. Future instruments will be far more sensitive, capable of detecting weaker signals from much greater distances. This means scientists will be able to observe mergers that occurred when the universe was much younger, allowing them to study how black holes and neutron stars formed during the early stages of cosmic history. By observing these ancient events, researchers can trace how the population of compact objects evolved over billions of years. They will be able to see whether neutron stars and black holes were more common in the early universe, how their masses changed over time, and how often they collided in different cosmic eras. This information will help refine models of galaxy formation and star evolution. Space-based gravitational wave observatories will also open a new observational window. Unlike ground-based detectors, which are sensitive to high-frequency signals from stellar mass mergers, space-based instruments will detect low-frequency gravitational waves produced by much larger systems. This includes mergers of supermassive black holes and long-lasting inspirals of compact objects around massive black holes. By combining data from ground-based and space-based observatories, scientists will be able to study black hole and neutron star interactions across a wide range of scales. This unified approach will provide a more complete picture of how gravity operates throughout the universe. Another major advancement will come from improved electromagnetic observatories. Future telescopes will be able to observe merger aftermaths in greater detail across multiple wavelengths. High-resolution X-ray telescopes will study accretion disks and jet formation. Infrared observatories will track the fading glow of kilonova explosions. Radio telescopes will map the interaction between merger debris and surrounding gas. This coordinated observation strategy, known as multi-messenger astronomy, allows scientists to study the same event using different types of signals. Gravitational waves reveal the motion of massive objects. Light reveals the behavior of matter and energy. Together, they provide a more complete understanding of what happens when a black hole eats a neutron star. Artificial intelligence and machine learning will also play a growing role in this research. As detection rates increase, the volume of data produced by observatories will become enormous. Automated systems will be needed to identify signals, classify events, and detect unusual patterns. These tools will allow scientists to respond quickly to new mergers and coordinate follow-up observations across the world. Advanced simulations will also become more realistic. Improvements in computing power will allow researchers to model mergers with greater precision. These simulations will incorporate more detailed physics, including magnetic fields, nuclear reactions, and relativistic effects. By comparing simulations with real observations, scientists can test theoretical models and refine predictions. Another important direction of future research involves understanding how black hole and neutron star mergers influence the long-term evolution of galaxies. Over cosmic time, repeated mergers contribute energy and momentum to galactic environments. This feedback can regulate star formation, shape gas distribution, and influence the growth of central black holes. Future surveys will map the locations of merger events relative to galaxy structures. This will reveal whether mergers occur more frequently in dense star clusters, galactic centers, or isolated regions. Such information will help scientists understand how environmental conditions affect the formation of compact object binaries. The study of mergers will also contribute to understanding cosmic magnetism. Neutron stars possess some of the strongest magnetic fields known. When they are disrupted by black holes, these magnetic fields interact with accretion disks and jets. Observing these interactions will help scientists understand how large-scale magnetic fields are generated and sustained in galaxies. Another promising area of research involves testing the limits of fundamental constants. By studying gravitational wave propagation over vast cosmic distances, scientists can test whether physical constants such as the speed of light and gravitational coupling remain consistent across the universe. Any deviation could indicate new physics beyond current models. Neutron star mergers may also provide insight into neutrinos, nearly massless particles that rarely interact with matter. These particles are produced in large numbers during extreme astrophysical events. Detecting neutrinos associated with mergers would add another layer of information, revealing details about nuclear reactions and energy transport processes. The possibility of detecting exotic phenomena also remains open. Some theoretical models predict the existence of hypothetical objects such as boson stars or dark matter cores inside neutron stars. If such objects exist, their presence could influence merger behavior in detectable ways. Observing unusual gravitational wave signatures or unexpected radiation patterns could point toward new forms of matter. Another future goal is the precise measurement of black hole properties. With improved detectors, scientists will be able to measure black hole mass, spin, and orientation with greater accuracy. This will help build detailed catalogues of black hole populations and identify patterns in how these objects form and evolve. These measurements may reveal whether black holes grow primarily through mergers, accretion, or both. They may also show how black hole spins are distributed, offering clues about the environments in which they formed. The study of neutron star interiors will also benefit from future observations. More precise measurements of tidal deformation and post-merger signals will allow scientists to narrow down the possible equations of state describing ultra-dense matter. This could lead to breakthroughs in nuclear physics and help explain the behavior of matter under extreme pressure. Beyond scientific discovery, these advances will also influence technology. The development of ultra-sensitive detectors requires innovations in optics, vibration isolation, quantum measurement, and data processing. These technologies often find applications in other fields, including medicine, navigation, and communication systems. The growing field of gravitational wave astronomy also inspires educational initiatives. Universities are developing new programs focused on astrophysics, data science, and instrumentation. Students trained in these areas gain skills that are valuable across many scientific and technical fields. Public engagement will also continue to grow. Visualizations of mergers, interactive simulations, and real-time detection announcements capture public attention. This interest helps promote science literacy and encourages curiosity about the universe. Another important aspect of future research is the ethical and philosophical impact of these discoveries. Understanding that space-time itself is dynamic and that massive objects collide and transform challenges traditional ideas about permanence and stability. It reshapes humanity's view of its place in the cosmos. The realization that elements in our bodies were forged in ancient cosmic collisions creates a sense of connection between life and the universe. It shows that human existence is deeply tied to processes that occur on scales far beyond everyday experience. Black hole and neutron star mergers also highlight the vast timescales of cosmic evolution. Events that occur in seconds can influence galaxies for millions of years. Signals that reach Earth today may have originated billions of years ago. This perspective encourages humility and long-term thinking. As detection rates increase, scientists will likely observe rare and unexpected types of mergers. Some systems may involve unusual mass ratios, extreme spins, or complex multi-object interactions. Each unexpected event will challenge existing theories and drive further research. Future observatories may also detect continuous gravitational wave signals from neutron stars orbiting black holes for extended periods before merging. These long-lasting signals would provide detailed information about orbital dynamics and gravitational interactions. The possibility of observing the formation of black holes in real time through collapsing neutron stars also remains an exciting prospect. Such observations would offer direct insight into the transition between neutron stars and black holes, revealing how matter behaves at the threshold of gravitational collapse. As these discoveries accumulate, scientists will be able to construct a more complete picture of the life cycle of compact objects, from star formation to supernova explosions, from neutron star creation to black hole mergers. The entire sequence of cosmic evolution becomes clearer. This growing understanding reinforces the idea that the universe is not static. It is constantly evolving, reshaped by countless interactions between matter and energy. Black hole and neutron star mergers represent some of the most dramatic expressions of this process. When a black hole eats a neutron star, it is not simply an isolated event. It is part of a larger cosmic narrative that connects the birth of stars, the creation of elements, the growth of galaxies, and the expansion of space-time itself. As humanity continues to observe and study these events, the boundary between known and unknown will continue to shift. Each detection brings new data, new questions, and new opportunities for discovery. In the final stage of this exploration, we will reflect on what these extreme cosmic events reveal about the ultimate nature of reality and how they may shape humanity's understanding of the universe in the centuries to come. As the understanding of black hole and neutron star mergers continues to deepen, scientists are beginning to see these events not only as extreme physical phenomena, but as windows into the deeper structure of reality itself. Each collision offers more than data. It offers perspective. It reveals how the universe organizes energy, matter, time, and space on the largest and smallest scales at once. One of the most profound realizations emerging from this research is that gravity is not simply a force pulling objects together. It is the geometry of space-time itself. When a neutron star spirals toward a black hole, the paths of both objects are shaped by curved space-time. Their motion is not guided by invisible strings, but by the bending of reality. This understanding transforms how scientists interpret cosmic motion. Orbits, mergers, and collapses are not just mechanical events. They are expressions of space-time responding to mass and energy. During the final moments of a merger, space-time becomes highly dynamic. Waves ripple outward, stretching and compressing the fabric of the universe. These gravitational waves do not move through space. They are movements of space itself. When detectors on Earth measure these waves, they are recording the vibration of reality caused by distant cosmic events. This connection between distant collisions and local measurement highlights how deeply interconnected the universe truly is. Another important insight comes from the study of extreme gravity near black holes. In everyday life, gravity feels constant and predictable. Near black holes, it becomes extreme and strange. Time slows. Distances stretch. Light bends dramatically. These effects are not theoretical curiosities. They are measurable and observable. Neutron star mergers allow scientists to observe these phenomena directly through gravitational wave signals and electromagnetic radiation. This opens new possibilities for testing the foundations of physics. Some theories predict that spacetime may have a granular structure at extremely small scales, similar to pixels in a digital image. Others suggest that spacetime may emerge from more fundamental quantum processes. If such effects exist, they may leave subtle signatures in merger signals. Detecting these signatures would revolutionize physics and change how scientists understand the nature of space and time. The interaction between black holes and neutron stars also raises deep questions about causality. Inside the event horizon, the concept of cause and effect becomes unclear. According to classical physics, all future paths lead toward the singularity. This challenges intuitive ideas about time flowing forward. Understanding how matter behaves as it crosses this boundary may reveal new insights into the nature of time itself. Some theoretical models propose that black holes may be connected to other regions of space-time through structures such as wormholes. While no direct evidence currently supports this idea, neutron star mergers provide environments where such exotic phenomena might occur. If wormholes or other space-time shortcuts exist, they could influence merger dynamics in subtle but detectable ways. Another fascinating aspect of these events is the relationship between entropy and black holes. Entropy is a measure of disorder and information content. Black holes are known to have enormous entropy, proportional to the area of their event horizons. When a neutron star is consumed, the entropy of the system increases dramatically. This process aligns with the second law of thermodynamics, which states that entropy tends to increase over time. Studying how entropy changes during mergers helps scientists understand the connection between gravity and thermodynamics. Some researchers believe that gravity itself may emerge from thermodynamic principles. If this is true, black hole mergers could reveal fundamental links between heat, information, and space-time geometry. Another important topic is the role of symmetry in these events. The universe often favors simple, symmetric solutions. However, real mergers are rarely perfectly symmetric. Differences in mass, spin, and orientation create complex dynamics. By studying how asymmetries affect merger outcomes, scientists gain insight into how small differences can lead to large effects. These asymmetries also influence the final motion of the merged black hole. In some cases, the newly formed black hole receives a powerful gravitational kick that sends it moving through space at high speed. This happens when gravitational waves are emitted unevenly in different directions. Such kicked black holes may be ejected from their original locations, wandering through galaxies or even escaping into intergalactic space. This phenomenon has important implications for galaxy evolution. If black holes are displaced from galactic centers, it can affect star formation, gas distribution, and long-term galactic stability. Understanding how often these kicks occur and how strong they are helps scientists model the life cycles of galaxies. The merger process also reveals information about how binary systems form in the first place. Some neutron star and black hole pairs form from massive stars born together. Others may form through dynamic interactions in dense star clusters, where gravitational encounters bring compact objects into close orbits. Each formation pathway leaves distinct signatures in merger statistics. By analyzing large numbers of events, scientists can determine which formation mechanisms dominate in different environments. This helps build a more complete picture of how stars, clusters, and galaxies evolve over time. Another emerging area of study involves the connection between mergers and cosmic background radiation. Some theories suggest that repeated mergers throughout cosmic history may contribute subtle background signals in gravitational waves. This gravitational wave background represents the combined effect of countless distant mergers occurring across the universe. Detecting and analyzing this background will allow scientists to study the overall merger rate throughout cosmic history. It will also provide information about early star formation and the growth of black holes in the young universe. Neutron star mergers also offer insight into the limits of matter stability. The transition from neutron star to black hole represents a boundary between two states of existence. Understanding this boundary helps refine models of collapse and extreme pressure behavior. It also informs studies of supernova explosions and stellar death. The extreme conditions present during mergers may also produce rare particle interactions. High-energy environments can create exotic particles or trigger rare nuclear reactions. While most of these effects occur far beyond current detection capabilities, future observatories may be able to detect associated signals, opening new windows into particle astrophysics. Another profound implication of these events is their role in shaping cosmic identity. The realization that heavy elements essential for life are produced in violent cosmic collisions connects biology with astrophysics. It suggests that life is not separate from cosmic processes, but deeply embedded within them. This connection changes how humanity views its place in the universe. It shows that the atoms making up living organisms were forged in extreme environments far beyond Earth. Every neutron star merger contributes to the chemical diversity of the cosmos, laying the groundwork for future planetary systems. Black hole and neutron star mergers also challenge the idea of permanence. Even the most stable objects eventually change. Stars die, neutron stars collapse, black holes merge and grow. The universe is in constant transformation. Understanding this process encourages a dynamic view of reality, where change is fundamental rather than exceptional. Another important insight involves scale. These events occur on scales far beyond everyday experience, yet their effects can be measured with instruments built by humans. This demonstrates the power of scientific inquiry and technological development. It shows that even the most distant and extreme phenomena can become part of human knowledge. The process of detecting and analyzing mergers also highlights the importance of global cooperation. Observatories around the world work together to identify signals and coordinate observations. This collaboration demonstrates how shared curiosity can unite people across cultures and borders. The cultural impact of these discoveries continues to grow. Black hole mergers inspire art, literature, and philosophical discussion. They influence how people think about time, space, and existence. They remind humanity that reality is far more complex and mysterious than everyday experience suggests. As scientists refine their understanding, new questions continue to emerge. What is the true nature of singularities? Does space-time have a smallest possible scale? How does information behave in extreme gravity? Each merger adds data, but also deepens the mystery. The future of this field promises even greater discoveries. With improved detectors, expanded observatory networks, and more advanced theoretical models, scientists will be able to probe deeper into the mechanics of these events. They may uncover new physical principles or confirm long-standing theoretical predictions. When a black hole eats a neutron star, the event is not just an astronomical curiosity. It is a fundamental interaction that touches nearly every branch of physics. It involves gravity, quantum mechanics, thermodynamics, nuclear physics, and cosmology. It connects the smallest particles with the largest structures in the universe. As research continues, these mergers will remain at the forefront of scientific discovery. They will continue to challenge assumptions, refine theories, and expand humanity's understanding of reality. In the final reflection, we will consider what these extreme events ultimately reveal about the universe itself, and how they may shape the future of cosmic exploration and human knowledge. As the story of black hole and neutron star mergers unfolds further, scientists begin to recognize that these events are not just endpoints of stellar evolution, but turning points that influence the future direction of cosmic structure. Each merger reshapes its environment in subtle and powerful ways, leaving long-lasting imprints that extend far beyond the moment of collision. One of the most important long-term effects is the redistribution of energy across space. When a neutron star is consumed, enormous amounts of gravitational and electromagnetic energy are released. While much of this energy escapes as gravitational waves and radiation, a significant portion interacts with surrounding matter. Gas clouds are heated, ionized, and sometimes pushed outward. Over time, these interactions change the temperature and density structure of entire regions of space. This redistribution of energy plays a role in regulating star formation. In some environments, shock waves from merger events compress nearby gas clouds, causing them to collapse and form new stars. In other cases, intense radiation heats the gas and prevents it from cooling, slowing, or stopping star formation. The balance between these two outcomes depends on local conditions such as gas density and magnetic field strength. Because of this, black hole and neutron star mergers become part of a larger feedback system that governs how galaxies evolve. They act alongside supernova explosions, stellar winds, and active galactic nuclei to shape the flow of matter within galaxies. Over billions of years, these combined processes determine the size, shape, and structure of galactic systems. Another important consequence involves the movement of black holes after mergers. As mentioned earlier, some mergers result in powerful gravitational recoil, causing the newly formed black hole to move rapidly through space. These wandering black holes may travel through star clusters or interstellar gas clouds, influencing their surroundings through gravitational interactions. As a moving black hole passes through a dense region, it can capture gas and dust, forming temporary accretion disks and emitting radiation. These travelling sources of energy may contribute to heating and turbulence within galaxies. Over long timescales, this motion can redistribute mass and influence the internal dynamics of galactic systems. The presence of wandering black holes also raises intriguing questions about hidden populations of compact objects. Many black holes may exist far from galactic centers, drifting quietly through space and remaining undetected. Neutron star mergers contribute to this population by creating new black holes and altering their trajectories. Understanding the distribution of these objects is important for building accurate models of galactic mass and gravitational structure. It may also help explain certain unexplained gravitational effects observed in some regions of space. Another area of interest is the influence of mergers on cosmic dust formation. Heavy elements produced during neutron star disruptions can combine with other materials to form microscopic dust grains. These grains play a crucial role in cooling gas clouds and enabling star and planet formation. Cosmic dust also affects how light travels through space, scattering and absorbing radiation. By contributing to dust production, mergers indirectly influence the appearance and evolution of galaxies. This connection highlights how even rare events can have widespread consequences. The role of mergers in enriching the intergalactic medium is also significant. Material ejected during collisions does not always remain within the host galaxy. Some of it escapes into intergalactic space, spreading heavy elements across vast regions. Over cosmic time, this process contributes to the gradual enrichment of the universe as a whole. This enrichment affects the formation of future galaxies and star systems. It influences the availability of elements necessary for rocky planets and complex chemistry. In this way, neutron star mergers contribute to the conditions that make diverse planetary systems possible. Another fascinating aspect of these events is their influence on cosmic radiation environments. High-energy particles produced during mergers can travel long distances through space. These particles may interact with interstellar matter, producing secondary radiation and altering chemical reactions in distant regions. While most of this radiation is absorbed or dispersed before reaching Earth, it plays a role in shaping the energy balance of the galaxy. Understanding these processes helps scientists model cosmic radiation backgrounds and their effects on astrophysical systems. The study of mergers also reveals information about the distribution of angular momentum in the universe. When neutron stars and black holes merge, angular momentum is redistributed through gravitational waves, radiation, and matter ejection. This redistribution influences the rotation of the resulting black hole and surrounding material. Angular momentum plays a crucial role in many astrophysical processes, including star formation, disk evolution, and jet production. By studying how mergers transfer angular momentum, scientists gain insight into the broader dynamics of cosmic systems. Another important implication involves the long-term stability of planetary systems. While mergers typically occur far from Earth, their effects can influence the overall environment of galaxies. Over billions of years, repeated energetic events shape the radiation background and gravitational structure that planetary systems experience. Understanding these influences helps scientists assess how stable environments suitable for life may arise and persist. It also provides context for evaluating how rare or common life-supporting conditions might be in the universe. The influence of mergers extends even to the large-scale structure of the universe. While individual events may seem small compared to the vastness of cosmic space, their cumulative effect over billions of years contributes to the energy budget of the universe. Gravitational waves, radiation, and matter redistribution all play roles in shaping cosmic evolution. Some researchers are exploring whether the combined gravitational wave background from countless mergers could influence the dynamics of space-time on very large scales. While this effect is likely subtle, it represents another example of how local events can contribute to global cosmic behavior. The growing catalogue of merger events also allows scientists to study statistical patterns. By analysing thousands of detections, researchers can identify trends in mass distribution, spin alignment, and merger frequency. These patterns reveal how compact objects form and evolve in different environments. Such statistical studies also help identify unusual events that deviate from expected behavior. These outliers often provide the most valuable scientific insights as they challenge existing theories and inspire new models. Another emerging field involves the search for electromagnetic precursors to mergers. Some theoretical models predict that neutron stars approaching black holes may emit subtle signals before the final collision. Detecting such signals would allow astronomers to anticipate mergers and prepare coordinated observations across multiple observatories. This predictive capability would significantly enhance multi-messenger astronomy. It would allow scientists to observe mergers from their earliest stages through final collapse and aftermath, providing a continuous view of the entire process. The continued development of real-time alert systems also plays a crucial role. When gravitational wave detectors identify a potential merger, automated systems notify observatories around the world within seconds. This rapid response enables telescopes to capture transient signals that fade quickly. These coordinated efforts demonstrate how modern astronomy relies on global cooperation and advanced communication systems. They also show how technology and science work together to expand human knowledge. Another profound implication of merger research is its impact on theoretical physics. Observations provide constraints that guide the development of new models. Theories that fail to match data must be revised or abandoned. This process helps refine understanding of fundamental laws and leads to more accurate descriptions of reality. As new data accumulates, scientists may discover phenomena that do not fit existing frameworks. Such discoveries could signal the need for new physical principles. In this sense, black hole and neutron star mergers act as catalysts for theoretical innovation. The philosophical implications of these events are also significant. They challenge traditional ideas about space, time, and matter. They reveal that reality is far more dynamic and interconnected than everyday experience suggests. The idea that space-time can vibrate, stretch, and carry information across the universe changes how people think about the nature of existence. It suggests that the universe is not just a stage on which events occur, but an active participant in those events. This realization encourages a deeper appreciation of the complexity and beauty of the cosmos. It also inspires questions about humanity's role in understanding and exploring this vast reality. As scientists continue to observe and analyze mergers, the field will continue to evolve. New discoveries will refine existing theories and open new lines of inquiry. The boundary between known and unknown will continue to shift. When a black hole eats a neutron star, the event leaves behind more than a larger black hole. It leaves behind data, insights, and inspiration. It reshapes cosmic environments, tests physical laws, and deepens understanding of the universe. In the final stage of this exploration, we will reflect on how these extreme events influence humanity's long-term relationship with space exploration and scientific discovery, and what they reveal about the ultimate fate of matter and energy in the cosmos. As the study of black hole and neutron star mergers matures, scientists begin to look beyond individual events and toward the long arc of cosmic history. These collisions are not isolated moments. They are part of a repeating cycle that stretches across billions of years, shaping how matter flows through the universe and how structures gradually evolve from simple beginnings into complex cosmic systems. One of the most important long-term patterns involves the gradual growth of black holes. When a black hole consumes a neutron star, its mass increases and its gravitational influence expands. Over time, repeated mergers allow black holes to grow from stellar-sized remnants into intermediate mass objects and, eventually, into the supermassive black holes found at the centers of galaxies. This growth process is slow but relentless, driven by countless interactions spread across cosmic time. These growing black holes influence their host galaxies in profound ways. Their gravity affects the motion of stars and gas near galactic centers. Their radiation and jets regulate star formation by heating or expelling surrounding material. This feedback loop creates a delicate balance that determines how galaxies develop their shapes, sizes, and internal structures. Understanding how neutron star mergers contribute to this process helps scientists explain why nearly every large galaxy appears to host a central supermassive black hole. It suggests that even small-scale mergers play a role in building the massive structures that dominate galactic cores. Another long-term consequence of these events is their role in redistributing matter across the universe. When neutron star material is ejected during a merger, it does not remain in one place. It spreads outward, mixing with interstellar gas and becoming part of new star-forming regions. Over time, this process smooths out chemical differences between regions and contributes to the overall enrichment of the cosmos. This gradual mixing influences the diversity of planetary systems. Regions enriched with heavy elements are more likely to form rocky planets and complex chemical environments. In this way, neutron star mergers indirectly shape the potential for life across the universe. The repeated release of gravitational waves from countless mergers also contributes to a subtle cosmic background. This gravitational wave background is similar in concept to the cosmic microwave background, which represents leftover radiation from the early universe. While much weaker and more difficult to detect, this background carries information about the history of compact object mergers throughout cosmic time. Detecting and analyzing this background will allow scientists to study the collective behavior of black hole and neutron star populations. It will reveal how merger rates changed as the universe aged, and how star formation patterns influenced the creation of compact objects. Another important long-term effect involves the stability of galactic disks. Energy injected by merger-related processes can create turbulence in interstellar gas. This turbulence affects how gas clouds collapse and how stars form. Over billions of years, such effects influence the thickness, rotation, and structure of galactic disks. This connection highlights how events occurring on relatively small scales can influence the large-scale appearance of galaxies. It also shows that galaxy evolution is shaped by many interconnected processes working together over vast timescales. Neutron star mergers also help scientists understand the life cycles of binary star systems. By studying merger rates and properties, researchers can infer how often massive stars form in pairs and how their interactions evolve over time. This information improves models of stellar populations and helps predict the frequency of future merger events. Another long-term implication involves the evolution of cosmic radiation environments. High-energy particles produced during mergers contribute to the overall radiation background of galaxies. Over time, this radiation influences chemical reactions in interstellar space and affects the physical conditions experienced by forming planetary systems. While these effects are subtle, they contribute to the broader environment in which stars and planets develop. Understanding them provides a more complete picture of cosmic evolution. The cumulative effect of mergers also influences the distribution of angular momentum in the universe. Each merger redistributes rotational energy through gravitational waves and matter ejection. Over billions of years, this process contributes to the overall angular momentum balance of cosmic structures. Angular momentum plays a crucial role in shaping rotating systems, such as galaxies, accretion disks, and planetary systems. Studying how mergers affect this balance helps scientists understand why cosmic structures rotate the way they do. Another intriguing long-term effect is the potential role of mergers in seeding large-scale magnetic fields. The intense magnetic activity associated with neutron star disruptions may contribute to the generation of magnetized plasma structures that later evolve into larger magnetic patterns within galaxies. Magnetic fields influence star formation, gas dynamics, and cosmic ray propagation. Understanding their origins remains an active area of research, and neutron star mergers may represent one of several contributing processes. The accumulation of observational data also allows scientists to explore rare and extreme cases. Some mergers involve unusually massive neutron stars or rapidly spinning black holes. Others occur in unusual environments such as dense star clusters or galactic halos. These rare events often provide the most valuable insights because they push physical models beyond typical conditions. By studying these outliers, scientists can test the robustness of existing theories and identify areas where improvements are needed. This process drives scientific progress and leads to more accurate descriptions of cosmic phenomena. Another long-term implication involves the potential detection of merger events in distant galaxies from the early universe. Observing mergers that occurred when the universe was only a few billion years old allows scientists to study how compact objects formed in environments very different from those of today. Early galaxies had lower metal content, different star formation rates, and more chaotic structures. Studying mergers from this era helps scientists understand how cosmic conditions influence the formation and evolution of neutron stars and black holes. The connection between mergers and cosmic history also extends to the study of reionization, a period when the first stars and galaxies ionized the surrounding intergalactic medium. While neutron star mergers are not primary drivers of this process, their energetic radiation may have contributed small but measurable effects. Understanding these contributions helps refine models of early cosmic evolution. Another important long-term effect is the role of mergers in shaping the gravitational landscape of galaxies. Each merger alters the local gravitational field, influencing the motion of nearby stars and gas. Over time, these changes accumulate, contributing to the dynamic evolution of galactic systems. This perspective emphasizes that galaxies are not static collections of stars. They are dynamic systems constantly influenced by internal and external events. Neutron star mergers represent one of many processes contributing to this ongoing evolution. The study of mergers also informs the search for habitable environments. By understanding how energetic events affect star formation and radiation backgrounds, scientists can better assess which regions of galaxies are more likely to support stable planetary systems over long periods. Regions with frequent energetic events may experience higher radiation levels, potentially affecting planetary atmospheres. Conversely, regions with moderate activity may offer more stable conditions. Understanding this balance helps guide future searches for potentially habitable worlds. Another long-term implication is the influence of mergers on cosmic structure formation simulations. Modern cosmological simulations aim to model the evolution of the universe from the Big Bang to the present day. Incorporating accurate models of black hole and neutron star mergers improves the realism of these simulations and helps match observational data more closely. These simulations allow scientists to test hypotheses about cosmic evolution and explore alternative scenarios. They also provide visual representations of how structures form and evolve over time. The continuous improvement of observational techniques ensures that future discoveries will refine current understanding. New detectors will reveal weaker signals, uncover hidden populations of compact objects, and provide more detailed measurements of merger dynamics. As this data accumulates, scientists will be able to build a more complete narrative of how black holes and neutron stars shape the universe across cosmic time. This narrative connects the smallest scales of nuclear physics with the largest scales of cosmology. When viewed from this long-term perspective, the collision between a black hole and a neutron star becomes more than a dramatic event. It becomes a building block in the ongoing story of cosmic evolution. It contributes to the growth of black holes, the enrichment of galaxies, the formation of planets, and the dynamic structure of space-time itself. Each merger leaves behind subtle traces that influence the future. Over billions of years, these traces accumulate, shaping the universe in ways that are both complex and interconnected. In the final reflection, we will bring together the physical, cosmic, and philosophical implications of these events, exploring what they reveal about the ultimate nature of reality and humanity's place within the vast cosmic landscape. As the exploration of black hole and neutron star mergers reaches its final horizon, a deeper understanding begins to take shape. These events are not only astrophysical phenomena, they are mirrors that reflect the fundamental nature of existence itself. They reveal how the universe operates at its most extreme limits, and how every part of reality, from the smallest particle to the largest galaxy, is connected to invisible threads of gravity and time. One of the most powerful realizations is that the universe is constantly recycling itself. Matter is not destroyed, it is transformed. A massive star becomes a neutron star. A neutron star becomes part of a black hole. The material ejected during the merger becomes part of future stars, planets, and potentially living worlds. This endless cycle of transformation connects the past, present, and future into a continuous cosmic flow. When a black hole eats a neutron star, it may seem like an act of pure destruction, but in reality, it is also an act of creation. It creates gravitational waves that reshape space-time. It creates heavy elements that enrich galaxies. It creates data that expands human knowledge. Even in the darkest regions of space, creation and destruction exist together. These events also remind humanity of the immense power hidden within the universe. The energy released during a single merger can exceed the combined output of billions of stars for a brief moment. Yet this power does not announce itself with sound or light that can be heard or seen directly by human senses. It travels silently through space-time as gravitational waves passing through planets and stars without resistance. This silent power reveals that reality operates far beyond the limits of ordinary perception. Another profound insight comes from the way these events challenge human intuition. In everyday experience, space feels empty and solid, Time feels constant and gravity feels gentle. Near black holes, these assumptions collapse. Space bends. Time slows. Gravity becomes overwhelming. Neutron star mergers expose these hidden layers of reality, showing that the universe is far stranger and more flexible than it appears. This understanding forces a shift in perspective. It shows that human experience represents only a narrow slice of what exists. Beyond this slice lies a vast domain of extreme physics where reality behaves in unfamiliar ways. Exploring this domain expands the boundaries of knowledge and challenges long-held assumptions about how the universe works. The detection of gravitational waves from mergers represents one of the greatest achievements in scientific history. For the first time, humanity has learned to listen to the universe, not through light, but through vibrations in space-time itself. This new sense opens an entirely different way of observing reality. It allows scientists to detect events that produce little or no light, revealing hidden aspects of the cosmos. This shift marks the beginning of a new era in astronomy. In the past, observation relied almost entirely on electromagnetic radiation. Now, gravitational wave astronomy adds a new dimension to cosmic exploration. Together, these tools provide a more complete picture of the universe. Another important realization is the role of technology in expanding human perception. Instruments capable of detecting distortions smaller than an atom's width now allow humans to measure events occurring billions of light years away. This achievement demonstrates the power of scientific cooperation, engineering innovation, and long-term research investment. These advances also highlight the importance of curiosity. The desire to understand black holes and neutron stars began as theoretical speculation. Over time, it led to the construction of observatories, the development of new technologies, and the discovery of phenomena that were once considered impossible to observe. Curiosity transformed imagination into measurable reality. The cultural impact of these discoveries continues to grow. Images of black holes, animations of space-time ripples, and recordings of gravitational wave signals inspire awe and wonder. They remind humanity that the universe is not static or simple, but dynamic and alive with motion. This sense of wonder plays an important role in shaping human identity. It encourages exploration, creativity, and philosophical reflection. It invites people to question their place in the universe and to consider how small yet significant humanity is within the vast cosmic landscape. Another powerful implication of these events is the realization that the laws of physics are universal. The same principles that govern motion on Earth also govern the behavior of black holes and neutron stars. This unity of physical law connects human experience with distant cosmic processes. It shows that reality operates according to consistent rules across unimaginable distances and scales. At the same time, black hole mergers highlight the limits of current understanding. Singularities, event horizons, and quantum gravity remain unresolved mysteries. Each new observation answers some questions while raising others. This continuous cycle of discovery and uncertainty drives scientific progress forward. The existence of unresolved mysteries is not a weakness. It is a strength. It keeps inquiry alive. It motivates further exploration and innovation. Neutron star mergers serve as reminders that the universe still holds many secrets waiting to be uncovered. Another important perspective involves the long-term future of the universe. As time passes, stars will burn out, galaxies will drift apart, and black holes will continue to merge and grow. These processes will shape the cosmic landscape far into the future. Understanding how mergers contribute to this evolution helps scientists model what the universe may look like billions or trillions of years from now. In this distant future, black holes may become some of the dominant structures in the universe. Their mergers will continue to reshape space-time and redistribute energy. Even as visible light fades from the cosmos, gravitational interactions will persist, carrying the legacy of ancient collisions forward through time. From a human perspective, these timescales are almost impossible to imagine. Yet studying mergers allows humanity to glimpse this vast future and understand the long-term trajectory of cosmic evolution. Another profound implication is the connection between life and cosmic events. The elements that make up living organisms were forged in stars and distributed through violent cosmic processes. Neutron star mergers contribute to this chemical diversity. This means that life on Earth is linked in a very real way to events that occurred billions of years ago in distant parts of the universe. This connection creates a sense of cosmic belonging. It shows that humanity is not separate from the universe, but part of its ongoing story. Every atom in the human body carries a history that stretches back to ancient stellar explosions and extreme cosmic collisions. The study of black hole and neutron star mergers also influences future space exploration. Understanding extreme gravity environments helps scientists plan missions that operate near compact objects or explore regions with strong gravitational fields. It also informs the design of navigation systems and space-based observatories. As technology advances, future generations may send probes closer to black holes, gathering data from regions that are currently unreachable. These missions could provide direct measurements of space-time curvature, radiation environments, and particle behavior near event horizons. Another long-term implication involves the philosophical interpretation of reality, the idea that space-time can bend, vibrate, and interact with matter, challenges traditional concepts of space as an empty container. It suggests that reality is more fluid and interconnected than previously imagined. This perspective influences how people think about existence, causality, and the nature of time. It encourages a view of the universe as a dynamic system in constant motion rather than a static backdrop for events. The story of black hole and neutron star mergers also highlights the importance of patience in scientific discovery. Many of the technologies required to detect these events took decades to develop. Theoretical predictions were made long before direct observation became possible. Persistence and long-term commitment made these discoveries possible. This lesson extends beyond astrophysics. It shows that complex problems often require sustained effort and collaboration across generations. Progress is built slowly, layer by layer, much like the cosmic structures scientists study. As humanity continues to observe these extreme events, the boundaries of knowledge will continue to expand. New discoveries will refine existing theories and inspire new questions. The process of exploration will never truly end. When a black hole eats a neutron star, it is not just a violent collision in a distant galaxy. It is a message from the universe. It tells a story about gravity, time, matter, and transformation. It reveals that reality is far more complex and interconnected than everyday experience suggests. These events remind humanity that the universe is vast, powerful, and full of mystery. They invite curiosity rather than fear. They encourage exploration rather than isolation. They inspire a deeper appreciation for the fragile yet remarkable existence of life within this cosmic environment. As the echoes of gravitational waves continue to travel across space, they carry with them the story of ancient collisions and future possibilities. They connect distant galaxies with small instruments on Earth, linking human curiosity with cosmic events. In this way, black hole and neutron star mergers become more than scientific phenomena. They become symbols of humanity's desire to understand the universe and its place within it. And as research continues, each new detection adds another chapter to this story, reminding us that the universe is not silent. It is constantly speaking through the language of space-time itself. As the final layer of understanding settles into place, black hole and neutron star mergers begin to reveal something even deeper than physical data. They reveal a pattern of cosmic storytelling. Each collision is a chapter in a universe that has been writing its history for billions of years, using gravity, energy, and time as its language. One of the most powerful realizations is that the universe evolves not through sudden perfection, but through continuous transformation. Nothing remains fixed. Stars are born, burn, collapse, and change form. Neutron stars exist for millions or billions of years before eventually merging or collapsing. Black holes grow slowly through repeated encounters. Even space-time itself is shaped and reshaped by these events. This constant motion shows that change is not an interruption of reality. It is reality. When a black hole eats a neutron star, the event demonstrates how endings become beginnings. The neutron star ceases to exist as a separate object, but its matter becomes part of a larger gravitational structure. Its elements spread outward. Its energy reshapes the surrounding region. Its gravitational waves travel across the universe, influencing distant detectors and expanding human knowledge. In this way, the universe does not erase history, it transforms it. This idea challenges the human tendency to see events as isolated. In cosmic terms, every action has consequences that ripple outward across space and time. A single merger can influence star formation millions of years later. It can contribute to the growth of a galaxy. It can shape the chemical environment that produces future planets. Everything is connected through long chains of cause and effect. Another important realization is that extreme events reveal hidden layers of reality. In ordinary conditions, the universe appears calm and predictable. Near black holes and neutron stars, reality behaves differently. Time stretches. Space curves, matter compresses into unfamiliar states. These environments expose features of physics that remain invisible elsewhere. By studying these extremes, scientists gain insight into the underlying structure of the universe. It is similar to how stress tests reveal the strength of materials. Extreme gravity reveals the strength and limits of physical laws. Without these rare events, many aspects of reality would remain hidden. The study of mergers also reveals how delicate the balance of cosmic systems can be. Small differences in mass, spin, or orbital alignment can dramatically change the outcome of a collision. A neutron star may be swallowed whole or torn apart, depending on subtle variations. This sensitivity shows that the universe is finely tuned, with complex interactions governing outcomes. This complexity encourages humility. Even with advanced technology and mathematical models, scientists continue to encounter unexpected behavior. Each discovery leads to new questions. The universe does not offer simple answers. It invites continuous exploration. Another deep implication involves the nature of observation itself. When scientists detect gravitational waves from a merger, they are not seeing the event directly. They are interpreting signals that represent distortions in space-time. This highlights the indirect nature of human perception. Reality is often accessed through layers of interpretation and measurement. Yet despite this indirect access, humans are able to reconstruct detailed cosmic events. This ability reflects the power of scientific reasoning and collaboration. It shows that understanding does not require direct experience. It requires careful observation, analysis, and creative interpretation. The global cooperation involved in gravitational wave astronomy also reveals something important about human society. These discoveries are not made by isolated individuals. They are achieved through networks of scientists, engineers, institutions, and governments working together across borders. This cooperation demonstrates how shared curiosity can unite people toward common goals. In a world often divided by conflict, scientific collaboration offers an alternative model of cooperation. It shows that knowledge can be a unifying force. Black hole and neutron star mergers, while occurring far from Earth, contribute to this global effort by providing common mysteries that inspire shared investigation. Another profound realization is the role of patience in cosmic understanding. Many of the theories that predicted black hole mergers were developed decades before observational confirmation. Researchers waited, refined models, improved technology, and persisted through technical challenges. This long-term commitment demonstrates that meaningful discovery often requires endurance and long vision. This patience mirrors the slow processes of the universe itself. Galaxies evolve over billions of years. Black holes grow gradually. Cosmic structures form through countless small interactions. The pace of science in some ways reflects the pace of the cosmos. Another important perspective involves the emotional impact of these discoveries. Learning that space-time can vibrate and that massive objects collide in distant galaxies can inspire awe and wonder. This emotional response is not separate from science. It plays a role in motivating curiosity and sustaining interest in exploration. Awe encourages people to ask questions, to seek understanding, and to expand their worldview. It helps bridge the gap between abstract equations and human experience. Black hole mergers provide powerful examples of phenomena that naturally evoke this sense of wonder. The educational impact of these discoveries is also significant. Students exposed to gravitational wave astronomy learn about physics, mathematics, engineering, and data science simultaneously. This interdisciplinary nature encourages new approaches to problem solving and innovation. As educational programs expand, future generations will grow up with an understanding that the universe is dynamic and accessible to exploration. This may inspire careers in science and technology, further accelerating progress. Another long-term implication involves the preservation of knowledge. The data collected from merger events is stored, shared, and analyzed by researchers worldwide. This collective memory becomes part of humanity's scientific heritage. It ensures that discoveries are not lost but built upon by future generations. This preservation reflects a broader human desire to understand and record reality. From ancient star charts to modern gravitational wave detectors, humans have always sought to document the cosmos. Black hole mergers represent the latest chapter in this long tradition. The philosophical implications of these events continue to expand. They challenge traditional ideas about beginnings and endings. They blur the boundary between matter and energy. They reveal that space-time itself is dynamic rather than static. These ideas influence how people think about existence. They suggest that reality is not composed of fixed objects, but of processes and interactions. Everything is in motion, constantly changing form and relationship. Another realization is the role of scale in shaping perspective. Human life unfolds on timescales of decades. Black hole mergers operate on timescales of millions or billions of years. Yet through observation, humans can connect these vastly different scales. This connection encourages a broader view of time and existence. Understanding cosmic timescales can shift priorities and values. It highlights the temporary nature of individual events and the long-term continuity of the universe. It encourages thinking beyond immediate concerns and considering the larger context of existence. The continued study of mergers will likely reveal new surprises. Unexpected signal patterns, rare event types, or unexplained phenomena may challenge existing models. These surprises will drive further research and inspire new theories. This process of discovery will not reach a final conclusion. Each answer leads to new questions. The universe remains open-ended, full of mystery and potential. When a black hole eats a neutron star, the event becomes more than an astronomical collision. It becomes a symbol of transformation, connection, and discovery. It represents the meeting point of extreme physics and human curiosity. It shows that even in the darkest regions of space, knowledge can be gained. Even in the most violent events, patterns can be found. Even in the most distant galaxies, humanity can detect echoes of cosmic activity. As gravitational waves continue to pass through Earth, they carry stories from distant times and places. They connect human instruments with ancient cosmic events. They remind humanity that it is part of a universe far larger and more complex than everyday experience suggests. In this ongoing dialogue between the cosmos and human understanding, Black hole and neutron star mergers stand as powerful voices. They speak through space-time itself, telling stories of gravity, matter, energy, and time. And as long as humanity continues to listen, to observe, and to question, these stories will continue to unfold, expanding the horizon of knowledge and deepening our understanding of the universe we inhabit. As the journey into black hole and neutron star mergers reaches its final depth, a quiet but powerful realization emerges. These events are not only about extreme gravity or distant galaxies, they are about patterns that repeat across nature itself. They reveal how systems evolve, how energy moves, and how complexity arises from simple physical rules. At the heart of every merger lies a fundamental principle: attraction. Gravity draws massive objects together, shaping orbits, triggering collisions, and guiding the flow of matter. This same principle operates on many levels of reality, from atoms binding into molecules to galaxies clustering into vast cosmic webs. Attraction governs structure. Black hole mergers represent the most dramatic expression of this universal tendency. Yet attraction alone does not tell the full story. Resistance also plays a role. Neutron stars resist collapse through quantum pressure. Magnetic fields resist compression. Radiation pushes outward against gravity. These opposing forces create tension, balance, and dynamic equilibrium. When a black hole finally overwhelms a neutron star, it represents the moment when gravity becomes dominant. But even in that dominance, resistance shapes how the event unfolds. This balance between opposing forces reflects a broader pattern seen throughout nature. Stability arises from tension. Motion arises from imbalance. Change arises when thresholds are crossed. Black hole and neutron star mergers make these abstract principles visible on a cosmic scale. Another profound lesson from these events involves the concept of limits. Neutron stars represent the maximum compression matter can sustain before collapsing into a black hole. This boundary marks the edge of known physics. When this limit is crossed, matter enters a regime where existing theories struggle to describe behavior accurately. Studying this boundary helps scientists understand where current models succeed and where new ideas are needed. It highlights the importance of exploring extreme conditions to uncover deeper laws of nature. Without pushing these boundaries, scientific progress would remain confined to familiar territory. The idea of limits also applies to measurement and observation. Detecting gravitational waves requires extraordinary precision. Scientists must isolate tiny signals from overwhelming background noise. This challenge mirrors the difficulty of extracting meaning from complexity. It demonstrates that knowledge often requires patience, careful design, and creative problem solving. Another important realization involves the flow of information. When a neutron star is consumed, information about its internal structure seems to disappear behind the event horizon. Yet physical laws suggest that information cannot be destroyed. This paradox forces scientists to rethink how information is stored and transmitted in extreme gravity. Some theories propose that information is encoded on the surface of the black hole's event horizon. Others suggest it is preserved in subtle quantum correlations. While no definitive answer exists yet, black hole mergers provide opportunities to test these ideas indirectly through gravitational wave patterns and radiation signatures. This focus on information connects astrophysics with computer science, quantum theory, and philosophy. It suggests that reality itself may be fundamentally informational in nature. If this is true, black hole mergers are not just collisions of matter, they are transformations of information, encoded in space-time. Another deep implication concerns the arrow of time. In everyday experience, time moves forward. Entropy increases. Systems evolve from order to disorder. Black hole mergers follow this pattern. They increase entropy and move the universe toward more complex states. Yet on microscopic scales, physical laws are often time-symmetric. This contrast raises questions about why time appears to flow in one direction on large scales. Studying mergers helps scientists explore this mystery by examining how entropy and gravity interact. The growth of black holes through mergers contributes to the long-term evolution of entropy in the universe. Over cosmic time, black holes may become dominant repositories of entropy. Understanding this process helps scientists model the ultimate fate of the cosmos. Another realization is the importance of scale in shaping physical behavior. On human scales, gravity feels weak. On cosmic scales, it dominates structure formation. On quantum scales, gravity becomes negligible compared to other forces. Black hole mergers bring these scales together, forcing scientists to consider how physical laws transition between regimes. This interplay between scales challenges traditional approaches to physics, which often treat different regimes separately. Mergers encourage a unified perspective that seeks connections between small-scale quantum behavior and large-scale gravitational dynamics. The study of these events also highlights the importance of approximation and modeling. Because direct experimentation is impossible, scientists rely on simulations and theoretical frameworks. These models are constantly refined as new data becomes available. This iterative process demonstrates how scientific knowledge evolves through continuous feedback between theory and observation. Another important lesson involves uncertainty. Despite remarkable advances, many aspects of black hole mergers remain uncertain. Exact interior structures, singularity behavior, and quantum effects remain unknown. Accepting this uncertainty is part of scientific progress. It encourages openness to new ideas and prevents rigid attachment to outdated models. The willingness to embrace uncertainty reflects a mature scientific culture. It recognizes that knowledge is provisional and subject to revision. Black hole mergers exemplify this process by constantly challenging existing assumptions. Another dimension of these events involves the human experience of discovery. Scientists who detect gravitational waves often describe emotional reactions ranging from excitement to awe. These emotions are not separate from scientific work. They reflect the deep human connection to exploration and understanding. This emotional engagement helps sustain long-term research efforts. It motivates scientists to persist through technical challenges and complex analysis. It also inspires public interest and support for scientific projects. The public response to black hole discoveries demonstrates the universal appeal of cosmic mysteries. People from diverse backgrounds find meaning and inspiration in learning about the universe. This shared curiosity creates opportunities for education, outreach, and cultural exchange. Another long-term implication of merger research involves the development of international infrastructure. Large observatories require global cooperation, shared funding, and coordinated operation. These projects demonstrate how large-scale scientific goals can bring nations together around common objectives. This cooperation extends beyond data sharing. It includes training programs, collaborative research initiatives, and joint technological development. Such partnerships strengthen the global scientific community and promote peaceful collaboration. The technological advancements driven by gravitational wave detection also influence other fields. Precision measurement techniques, advanced computing methods, and improved sensor technologies find applications in medicine, engineering, and environmental monitoring. This demonstrates how fundamental research can produce practical benefits. Another important realization involves the resilience of scientific inquiry. Despite setbacks, failed experiments, and technical challenges, progress continues. Each obstacle leads to new solutions and improved methods. Black hole merger research exemplifies this resilience through decades of theoretical work and technological development. This persistence reflects a broader human trait, the desire to understand and explore. It shows that curiosity is a powerful driving force capable of overcoming significant challenges. As data accumulates and models improve, scientists will likely uncover deeper patterns governing cosmic evolution. These patterns may reveal new symmetries, conservation laws, or relationships between fundamental forces. Black hole mergers serve as laboratories for testing these ideas under extreme conditions. The future of this field promises continued discovery. New detectors, improved analysis techniques, and expanded observational networks will reveal events that were previously undetectable. Each new detection adds another piece to the cosmic puzzle. As humanity continues to explore these phenomena, the boundary between the known and unknown will keep shifting. This process will not lead to a final answer, but to an ever-deepening understanding of reality. When viewed in this broader context, black hole and neutron star mergers become symbols of transformation. They represent the dynamic nature of the universe and the continuous flow of matter and energy. They show that endings are not final, but part of larger cycles of change. They also symbolize humanity's quest for knowledge. Each detection represents a triumph of curiosity, collaboration, and innovation. Each new insight expands the horizon of understanding. In the end, these events remind humanity that the universe is not distant or detached. It is connected to every atom, every star, and every observer. The same physical laws that govern black hole mergers also govern the behavior of matter on Earth. This connection creates a sense of unity between human experience and cosmic processes. It suggests that understanding the universe is also a way of understanding ourselves. As gravitational waves continue to ripple across space-time, they carry with them messages from ancient collisions. These messages tell stories of gravity, energy, and transformation. They invite humanity to listen, to learn, and to explore further. And as long as curiosity remains alive, the dialogue between the cosmos and human understanding will continue, revealing new layers of reality and deepening the story of existence itself. As the final chapter of understanding begins to form, black hole and neutron star mergers reveal one last, powerful truth. The universe is not built from isolated objects, but from relationships. Everything that exists is shaped by interaction. Stars influence galaxies. Galaxies influence cosmic structure. Gravity links distant regions of space through invisible connections. These mergers make that web of relationships visible in the most dramatic way possible. When two extreme objects spiral together, their interaction reshapes the space around them long before contact occurs. Long before matter touches matter, space-time itself begins to respond. Distances stretch, orbits tighten, energy flows outward. This demonstrates that relationships, not just objects, define reality. What matters is not only what something is, but how it interacts with everything around it. This realization shifts the focus of cosmic understanding. Instead of seeing the universe as a collection of separate entities, scientists increasingly view it as a network of processes. Matter flows, energy transfers, information propagates. Black hole mergers become nodes of intense interaction where multiple processes converge at once. Another deep implication of this perspective is that no event is truly local. Even the most distant merger influences the universe beyond its immediate environment. Gravitational waves carry information across billions of light years. Radiation alters surrounding space. Ejected matter becomes part of new systems. Every collision sends ripples outward, connecting distant regions through shared history. This interconnectedness challenges the idea of isolation. It suggests that every part of the universe is linked, directly or indirectly, to every other part. While these connections may be weak or subtle, they exist nonetheless. Black hole mergers provide some of the clearest evidence of this cosmic unity. Another important realization involves the role of symmetry and imbalance. Perfect symmetry rarely exists in nature. Slight differences in mass, spin, or orientation create complex outcomes. These imperfections drive diversity and complexity. In mergers, smaller symmetries determine whether matter is ejected, whether jets form, and how gravitational waves are emitted. This principle extends beyond astrophysics. Complexity in biological systems, climate patterns, and social structures often arises from small variations and imbalances. Black hole mergers illustrate how complexity emerges naturally from simple physical rules combined with imperfect symmetry. The study of these events also highlights the importance of thresholds. Neutron stars remain stable only up to certain limits. When mass or pressure crosses a critical boundary, collapse occurs. These thresholds represent turning points where gradual change becomes sudden transformation. Threshold behavior appears throughout nature. Water freezes at a specific temperature. Chemical reactions activate at certain energy levels. Societies undergo rapid change when conditions reach critical points. Black hole mergers provide a cosmic example of this universal pattern. Another profound insight involves the role of feedback loops. Mergers influence galaxy evolution. Galaxy environments influence merger rates. Star formation affects the creation of compact objects. Compact object mergers affect chemical enrichment and radiation environments. These processes form interconnected feedback systems that shape cosmic history. Understanding these feedback loops helps scientists model how the universe evolves over time. It shows that no single process operates independently. Instead, cosmic evolution emerges from the interaction of many processes working together across different scales. Another important theme is the balance between predictability and uncertainty. While physics allows scientists to predict general merger behavior, individual events often contain surprises. Unexpected signal patterns, unusual mass ratios, or rare configurations challenge existing models. This balance reflects a fundamental feature of reality. Laws provide structure, but complexity introduces unpredictability. Black hole mergers demonstrate how order and uncertainty coexist. They follow physical rules, yet produce unique outcomes in each case. The presence of uncertainty does not weaken scientific understanding. Instead, it enriches it. It encourages continuous refinement of models and openness to new ideas. It keeps exploration alive and dynamic. Another significant implication involves the way humans conceptualize time. Gravitational waves from distant mergers represent signals that began traveling billions of years ago. When detected on Earth, they provide direct contact with ancient events. This creates a bridge between past and present, allowing humans to observe history as it unfolds. This ability to access deep time changes how people think about history. It extends historical awareness beyond human civilization to cosmic evolution. It encourages a broader view of time that includes stellar life cycles, galaxy formation, and the expansion of the universe. Understanding deep time also fosters patience and perspective. It highlights how brief human existence is compared to cosmic timescales, yet it also shows how meaningful human observation can be, even on such vast scales. Another profound realization is the role of interpretation in shaping knowledge. Gravitational wave data does not arrive as images or sounds. It arrives as abstract signals that must be analyzed and interpreted. Scientists use mathematical models to translate these signals into physical events. This process demonstrates that understanding reality often requires layers of interpretation. Data becomes meaning through analysis, theory, and collaboration. Black hole mergers remind humanity that knowledge is constructed through careful reasoning rather than direct sensory experience alone. Another important dimension is the ethical responsibility associated with powerful knowledge. As humanity gains greater understanding of extreme cosmic phenomena, it also gains technological capabilities. These capabilities must be guided by thoughtful decision-making to ensure they are used responsibly. While gravitational wave research itself is not directly dangerous, the technologies developed through advanced physics can have broader implications. Recognizing this responsibility encourages ethical reflection alongside scientific progress. The exploration of black hole mergers also encourages interdisciplinary thinking. Astrophysics intersects with quantum mechanics, nuclear physics, computer science, and engineering. This cross-disciplinary approach fosters innovation and new perspectives. Such collaboration breaks down traditional boundaries between scientific fields. It creates opportunities for new ideas to emerge at the intersections of disciplines. Black hole merger research exemplifies this trend toward integrated knowledge. Another key insight involves the role of storytelling in science. While equations describe physical processes, narratives help communicate meaning. Describing mergers as cosmic events with dramatic sequences helps people understand and engage with complex ideas. Storytelling does not replace rigorous analysis, but it complements it. It allows scientific discoveries to reach wider audiences and inspire curiosity. Black hole mergers provide compelling stories that capture imagination while remaining grounded in evidence. Another long-term implication is the preservation of curiosity itself. In a world filled with practical concerns, cosmic exploration may seem distant or abstract, yet it plays a crucial role in maintaining humanity's sense of wonder and exploration. Curiosity drives innovation, creativity, and cultural growth. It encourages people to look beyond immediate problems and consider larger questions about existence. Black hole mergers represent one of the most powerful sources of cosmic curiosity. The continued study of these events will also shape future generations of scientists. Students inspired by gravitational wave discoveries may pursue careers in physics, engineering, and data science. This new generation will bring fresh perspectives and ideas, further advancing the field. As technology improves, future researchers may detect phenomena that current instruments cannot observe. They may uncover subtle effects related to quantum gravity, space-time structure, or unknown particles. Each new discovery will expand the boundaries of knowledge. Another profound implication involves the role of humanity as observers of the universe. By detecting and interpreting cosmic events, humans become participants in the universe's self-awareness. The universe, through human consciousness, becomes capable of observing itself. This idea carries philosophical significance. It suggests that consciousness and cosmic processes are not entirely separate. Instead, they form part of a larger system in which observation and existence are connected. Black hole mergers, observed through advanced instruments, represent moments when this connection becomes especially clear. Distant events influence local detectors, which influence human understanding. The universe and humanity become linked through information exchange. This perspective encourages a sense of responsibility toward knowledge. It reminds humanity that understanding the universe is not just about collecting data, but about integrating that understanding into culture, education, and decision-making. Another important realization is that discovery does not eliminate mystery. Even as scientists learn more about mergers, new questions arise. What lies inside singularities? How does space-time behave at the smallest scales? What is the ultimate fate of information? These unanswered questions ensure that exploration will continue. They prevent scientific inquiry from becoming stagnant. Black hole mergers serve as gateways to deeper mysteries rather than final answers. In the broader cosmic context, these events represent moments of intense transformation. They reshape space-time, redistribute matter, and generate signals that travel across the universe. They contribute to the ongoing evolution of cosmic structure. When viewed from this perspective, black hole and neutron star mergers become symbols of change, connection, and continuity. They remind humanity that reality is not static, but constantly evolving. They also highlight the power of observation and understanding. Through careful measurement and analysis, humans can access events that occur billions of light years away. This capability demonstrates the remarkable potential of scientific inquiry. As gravitational waves continue to reach Earth from distant mergers, they carry with them stories of cosmic transformation. Each signal represents a chapter in the universe's long history. Each detection adds another layer of understanding. In this ongoing dialogue between humanity and the cosmos, black hole and neutron star mergers play a central role. They connect extreme physics with human curiosity. They reveal the hidden dynamics of space-time. They expand the boundaries of knowledge. And as long as humanity continues to observe, question, and explore, these cosmic events will remain powerful guides, leading toward deeper understanding of the universe and our place within it. As the journey reaches its final horizon, the meaning of black hole and neutron star mergers becomes clear in a way that goes beyond equations and data. These events are not just violent collisions in distant galaxies. They are reminders of how the universe builds complexity, how it transforms itself, and how every part of reality is woven into a continuous cosmic story. At the deepest level, these mergers reveal that the universe is not static. Nothing remains frozen in time. Even the densest, most extreme objects eventually change. Neutron stars, once thought to be permanent remnants of stellar death, can be torn apart or collapsed into black holes. Black holes themselves grow, merge, and reshape their surroundings. This continuous transformation shows that stability is temporary and motion is fundamental. This idea challenges the human desire for permanence. In everyday life, people seek lasting structures, stable systems, and predictable patterns. The cosmos, however, operates on a different rhythm. It embraces change as a natural state. Black hole mergers demonstrate that even the most extreme forms of matter are part of a larger cycle of evolution. Another powerful lesson from these events is the role of patience in understanding reality. Many of the signals detected today began their journey billions of years ago. They traveled silently through space, crossing galaxies and cosmic voids, before finally reaching Earth. This reminds humanity that discovery often involves waiting, persistence, and long-term commitment. The fact that humans can detect and interpret these ancient signals speaks to the remarkable capacity of scientific inquiry. It shows that knowledge can bridge vast distances and timescales. It demonstrates that curiosity, combined with technology and cooperation, can overcome the limitations of human perception. Black hole and neutron star mergers also highlight the importance of listening to the universe in new ways. For centuries, astronomy relied almost entirely on light. The detection of gravitational waves introduced a new sense, allowing humanity to hear the vibrations of space-time itself. This expanded perception reveals aspects of reality that were previously hidden. This new form of observation encourages a broader view of exploration. It suggests that there may be other ways to detect cosmic phenomena that have not yet been imagined. The universe may carry information through channels that science has not yet learned to interpret. Mergers represent only the beginning of this expanded cosmic dialogue. Another profound implication involves the role of limits. Neutron stars represent the boundary between stable matter and gravitational collapse. Black holes represent the boundary beyond which classical physics breaks down. Studying these boundaries helps scientists understand where existing theories succeed and where new ideas are needed. Boundaries are not just obstacles, they are opportunities for discovery. They mark regions where new physics may emerge. Black hole mergers allow humanity to probe these boundaries directly, using nature's most extreme laboratories. These events also reveal how small-scale processes influence large-scale outcomes. The behavior of particles inside neutron stars affects how matter is ejected during mergers. This ejected matter influences galaxy chemistry. Galaxy chemistry influences star formation. Star formation influences future merger rates. This chain of influence demonstrates how microscopic and macroscopic processes are connected. This interconnectedness encourages a holistic view of the universe. Instead of studying isolated phenomena, scientists increasingly focus on systems and relationships. Black hole mergers serve as central nodes in these cosmic networks, linking multiple processes across different scales. Another important realization is the role of randomness and chance. While physical laws govern general behavior, the exact details of each merger depend on initial conditions that may vary widely. Small differences in orbital alignment, mass distribution, or environmental factors can lead to very different outcomes. This sensitivity to initial conditions introduces an element of unpredictability. It shows that even in a universe governed by laws, there is room for variation and uniqueness. Each merger becomes a singular event with its own characteristics and story. This uniqueness adds richness to cosmic evolution. It ensures diversity in outcomes and prevents the universe from becoming monotonous. Black hole mergers exemplify this diversity by producing a wide range of signals and aftermaths. Another deep insight involves the relationship between destruction and creation. When a neutron star is consumed, it is destroyed as an individual object, yet the process creates new structures, new elements, and new forms of energy. Destruction becomes a pathway to creation. This pattern appears throughout nature. Forest fires destroy old growth but create conditions for new life. Volcanic eruptions reshape landscapes and enrich soil. In the cosmos, mergers destroy stars but enrich galaxies. This dual role of destruction and creation reflects a universal principle of transformation. Understanding this principle encourages a more balanced view of change. It shows that endings are not final, but part of larger cycles. Black hole mergers illustrate this idea on the grandest possible scale. Another powerful implication involves the nature of observation and meaning. When scientists detect gravitational waves, they translate abstract data into stories about distant events. This act of interpretation transforms raw signals into understanding. It shows that meaning emerges through interaction between observer and phenomenon. This relationship between observation and meaning extends beyond science. It reflects how humans engage with reality in general. Understanding is not simply received. It is constructed through analysis, reflection, and communication. Black hole mergers therefore become not only physical events, but sources of meaning that shape human culture and thought. They inspire art, philosophy, and storytelling. They influence how people imagine the universe and their place within it. Another important realization is the role of humility in cosmic exploration. The universe continually reveals how limited human understanding can be. Each discovery opens new questions. Each answer leads to deeper mysteries. This endless process encourages humility and openness. Humility does not weaken science, it strengthens it. It keeps inquiry flexible and adaptable. It prevents rigid attachment to incomplete models. Black hole mergers remind scientists that even the most advanced theories are provisional and subject to revision. Another profound implication is the recognition that the universe is accessible, not distant. While black hole mergers occur far away, their signals reach Earth. They influence detectors, inspire research, and shape knowledge. This connection shows that distance does not equal separation. The universe is connected through physical laws that operate everywhere. This accessibility encourages exploration. It suggests that even the most extreme and distant phenomena can be studied and understood. It reinforces the idea that the universe is not beyond reach, but open to investigation. Another important aspect is the role of collective effort. Gravitational wave detection requires coordination among observatories, researchers, and institutions worldwide. This collaboration demonstrates that scientific progress is a shared achievement. This collective effort reflects a broader truth about knowledge. Understanding grows through cooperation rather than isolation. black hole mergers become examples of how shared curiosity can unite people toward common goals. The technological legacy of these discoveries will continue to influence society. Advances in precision measurement, data processing, and sensor technology will find applications in other fields. This demonstrates how fundamental research can produce unexpected benefits. Another lasting impact involves education. Students exposed to gravitational wave astronomy learn not only physics, but also critical thinking, problem solving, and interdisciplinary collaboration. These skills extend beyond science and contribute to broader intellectual development. As future generations build on current discoveries, new questions will emerge. How does space-time behave at the smallest scales? What is the true nature of singularities? How does information persist in extreme gravity? These questions will guide future research. Black hole mergers will continue to serve as natural laboratories for exploring these mysteries. They provide real-world tests of theoretical ideas and opportunities to refine understanding. In the broader context of cosmic evolution, these events represent moments of intense transformation. They shape galaxies, influence chemical composition, and contribute to the dynamic structure of the universe. They are part of the ongoing process that has shaped reality from the Big Bang to the present. From a human perspective, these events also shape worldview. They encourage people to think beyond everyday experience and consider the vastness of existence. They inspire curiosity, wonder, and reflection. They remind humanity that it exists within a universe far larger and more complex than daily life suggests. Yet they also show that humanity is capable of understanding and exploring this universe through knowledge and cooperation. When a black hole eats a neutron star, the event becomes a symbol of cosmic transformation. It represents the power of gravity, the flexibility of space-time, and the endless cycle of change that defines the universe. It also represents humanity's desire to understand reality. Each detection, each analysis, and each theory contributes to a growing body of knowledge that connects Earth to distant galaxies. As gravitational waves continue to ripple through space-time, they carry with them the echoes of ancient collisions. These echoes tell stories of creation, destruction, and transformation. They invite humanity to listen, to learn, and to continue exploring. In the end, black hole and neutron star mergers remind humanity of one essential truth. The universe is not silent, not static, and not separate from those who observe it. It is dynamic, interconnected, and constantly revealing new layers of meaning. And as long as curiosity remains alive, the story of the cosmos will continue to unfold, carrying humanity forward into deeper understanding of reality itself.